and welcome to Storms of the Solar System and Beyond. I'm Jada Arney from NASA Goddard, and I want to welcome you all here. And we're excited for this really fantastic panel of some expert NASA scientists who will be delighted to speak to you about these interesting topics related to weather and climates on solar system bodies and bodies beyond the solar system. I'm also excited to announce that we are streaming live on Facebook Live, and we've got an audience around the world. So we encourage questions from our online audience as well as the audience in the room. This event is also part of a global event called the Lookup event. That's part of Dr. Mae Jamison's 100-year Starship Foundation. And as part of this, after this event, we'll have stargazing outside here at the Gilruth Center at NASA Johnson. So for those in the live audience here, we invite you to go out back to the soccer fields on the south side of this building and enjoy looking up at the night sky with telescopes provided by the Houston Astronomical Society. And with that, I'm going to turn it over to our panel, and again, welcome.
Well, good evening, everyone. My name is Elizabeth Tasker, and I am at the Japan Aerospace Exploration Agency near Tokyo. And with me today to discuss storms of the solar system and beyond, I have 4 planetary and solar scientists. On the far left, I have Holly Gilbert, who is the director of the Heliophysics Science Division at NASA Goddard Space Flight Center. Holly's research involves dynamic activities on the sun and phenomena such as coronal mass ejections, which I think she'll tell us about later. Next to her, I have David Crisp. He is an atmospheric physicist at NASA Jet Propulsion Laboratory. He has spent his career chasing photons through the atmosphere of Venus, Earth, and Mars, and more recently, exoplanets. To my right, I have Geronimo Villanueva, is a planetary scientist at NASA Goddard Space Flight Center. He specializes in hunting for astrobiologically important molecules in planetary atmospheres in the solar system and beyond. And last but not least, I have Laurie Glaze, who is the acting director of the Planetary Science Division at NASA headquarters. Laurie studies the importance of volcanism on planetary climates and has spent the last decade developing mission concepts for studying Venus's atmosphere. So when we think about storms, we normally think about lashing rain, wind, and especially this afternoon, thunder and lightning. But these phenomena are very much associated with the Earth. They're concerned with our atmosphere of nitrogen, oxygen, carbon dioxide, and the reaction with the rocks on the Earth, which are predominantly silicates. So if we leave the Earth and go to one of our neighboring planets, do we have storms there we recognize? Is a weather system similar to our own? Or is it a storm only in name and something truly alien? Maybe the best place to start this question would be one of our 2 nearest neighbors, Mars. Now, any fans of The Martian will associate Mars with dust storms. Moreover, if you've been following NASA news, you may have heard that we've lost contact with the Opportunity rover due to a dust storm on Mars. So I'm going to start with maybe Geronimo to ask the question, is dust storms common weather on Mars? And what would it be like to be in one?
Yes, well, thank you, Larry. So, as you know, I've seen Mars now is bigger than anything in the last 14 years. So Mars is very big, and if you look at it right now, normally it looks red, but now it looks orange. And it's orange because it's being covered by a full dust storm that is covering the whole planet. And Mars actually develops that every 2 years, which Mars takes 2 years to go around the sun. So once a year, for a Martian year, it will develop a global dust storm. And we don't really know what is the process that actually drives this, or what is the mechanism specifically what drives, but it happens always at the same time, after the northern summer time on Mars. And the thing is, it engulfs the whole planet, and it's made of dust, not like our planet that has a lot of water vapor and liquid water. In the case of Mars, it's just particles that go across the whole planet and transform the whole planet, even if you're on the surface. That's why we have Opportunity rover there that is using solar panels to get light and to be alive in some way. Now, with all the dust covering the surface, now the rover has lost communication. We're hopeful that by the moment the storms subdue, the rover will communicate back and say, hey, we're still alive, we're taking data. It has done it before, so we are hopefully it will return back to activity.
Thanks very much. David, would you like to add anything? What is being in a dust storm like?
Well, on Mars, the atmosphere is only about 1% as dense as the atmosphere on the Earth. So even when the winds are howling, they're not pushing on you very hard, but they're carrying dust. And if we have winds that are whipping by at 70 miles an hour, carrying dust made of rock, you're being sandblasted. That's what it would be like. It would get into everything. It gets into our circuits and our robot arms and in our cabling and all through our cameras on our Mars rovers. So it's really a pretty dramatic event, even in this very, very thin atmosphere. As the storm starts to abate, as it is now, the dust just starts falling out. But it is super fine dust, and it takes a while to fall out. And unfortunately, some of that dust will fall on the poor solar panels of the Opportunity rover, making it just a little bit harder for it to wake back up. I helped design those solar panels, so I'm rooting for it. Come on, girl, you can do it one more time. It's pulled out before, so I'm waiting for what I call the MAID service to come in. These are the little dust devils that go across Mars. This is another dust phenomenon we regularly see on Mars, and I'm waiting for those to come clean up the mess and make those solar panels nice and clean again.
So, dust on Mars. Now, what happens if we go the other direction towards the sun and go to our other neighbor, Venus? Now, Mars is actually a pretty small planet, but Venus is very close to the Earth in its size, but it has a much thicker atmosphere. Laurie, what is weather like on Venus?
So Venus is a really interesting and bizarre place in our solar system. I heard someone say one time, if there wasn't a Venus in our solar system, we would have never imagined one could have existed. Because at the surface of Venus, as you say, Elizabeth, the atmosphere is so dense and so thick. The atmospheric pressures at the surface are about 90 times what we have here on Earth. The temperatures at the surface are around 750 degrees Fahrenheit, hot enough to melt lead. And so at the surface, you can just imagine the crushing pressures, the incredibly dense atmosphere, and those hot, hot temperatures. But it's interesting that Dave was talking about how Mars's atmosphere is about 1% of the density of Earth's. Well, with all of that pressure, all of the pressure, atmospheric pressure at the surface of Venus, the winds move very, very slowly on Venus. They may only move about a mile per hour at the surface. But because the atmosphere is so dense, it would feel like hurricane-force winds blowing against you, even at only 1 mile per hour, just because there's so much mass in that dense atmosphere. As you go up in Venus's atmosphere, the winds start to pick up, but the pressure starts to drop, and the density drops as you go higher and higher. And as you get to the top of the cloud layer, at that point, the pressure's dropped way below what we're used to here at the surface of Earth. But there, the winds are moving at about 100 meters per second at the top, or 150 meters per second. And so that is pretty fast. So again, even though now it's lower density, again, hurricane force winds at the top of the atmosphere. So you pretty much have hurricane force winds throughout the whole column of Venus's atmosphere.
So we've only been down to the Venetian surface, was it the late 1970s? Most of our experiments have been concerned in the more upper atmosphere. So, Dave, when we do that, we have to be worried about these very fast winds above the surface. Is that right?
Yes, the entire cloud layer of Venus, this layer that's about, 30 miles above the surface, is rotating about 60 times as fast as the solid surface of the planet, almost as a solid shell. It's as if somebody didn't get the memo that you're only supposed to rotate once every 242 days. They rotate once every 4 days. That's an incredible weather phenomena that still has pretty much evaded our ability to explain it with any of our best weather prediction models. So that's pretty fascinating by itself. But within those clouds, in addition to those very large winds that are going horizontally, we also have big winds going vertically. We flew a couple of weather balloons in the Venus atmosphere back in 1985 with the Soviets and the French. And as they were flying around in what we call the middle cloud layer, about 50 kilometers or about 30 miles above the surface, they were constantly being jerked upward at up to about 6 miles an hour upward, then 6 miles an hour downward. If you were going through a thunderstorm in an airplane, it wouldn't be that violent. So it's really, really dramatic. So on Venus, we have all kinds of interesting phenomena going on, and we're still trying to understand how some of it works.
So there's some pretty dramatic weather, but also quite recognizable. You know, you have a planet with a surface, and there's some strong things going on in the atmosphere. But a term we also sometimes hear is the term solar storms. So these must be to do with the sun, but the sun has no surface or air that we think of. Holly, tell us, what is a solar storm, and why does it affect any of the planets?
When we're talking about solar storms, we really have to consider the fact that the sun is a completely different beast than the bodies we've been talking about. And I'm laughing and hearing about 30 miles scales because we're talking major scales, much larger. But the main difference is that the sun is this big ball of extremely hot gas, what we call plasma, and it's rotating. And more importantly and relevant to what I'm going to talk about in a second, space weather, is the fact that it's magnetically driven. It has magnetic fields that are generated in its core as it's rotating, and these magnetic fields also rotate at different speeds when they're at the surface. And this is important because I don't know what's causing that. The magnetic fields themselves interact when they're twisting like that in a very, very violent process, a physics process that creates what we call these solar storms, these huge bubbles of mass and magnetic field lines blowing away from the sun at sometimes over 4 million miles an hour. So we're talking major, the mother of all storms. And these are called coronal mass ejections. They originate in the outer atmosphere of the sun called the corona. They're also oftentimes associated with solar flares, which most people have heard of, which is also a very explosive phenomena. Now, this is all relevant because if these things are headed towards the planets, the sun's domain reaches beyond Pluto, so it's a huge domain. This affects all the planets. We're embedded in that outer atmosphere. Then we feel the effects of these things, and also there's a constant solar wind that's coming from the sun. So our magnetic field here on Earth interacts with these big bubbles and can cause space weather effects. We're protected here on the surface, but it can cause other effects. And the other planets also have reactions to this. So it's kind of the main, what I like to think, the main star of the solar system, of course.
So what I'm going to do is I'm going to pose one more question to all our panelists, and then I'd like to take some questions to the audience. So please start thinking about what you would like to ask them. So the question I really want to ask is, what we've considered so far is the planets and the sun as they are today. And it paints a pretty clear picture. You've got one planet, the Earth, that is habitable, and it's flanked by two other planets which have very different storms and atmosphere and weather conditions, which makes them utterly uninhabitable, at least to us. But was that always true? Like, in the past, were things different? And in the future, will things be different again? If we want to understand perhaps our own habitability or the habitability of other planets, we need to look at this as a process. So maybe we should start at the center of our solar system and work out. And I'm going to go back to you, Holly, and say, was the sun always the brightness it is now? And what will happen in the future? And why should the planets around it care?
Well, the sun is sort of this happily middle-aged star. It hasn't always been this way. 4.5 billion years ago, it was different. It was young, it was very active, but it was fainter. Now, the reason I'm saying it was more active because that is very relevant in terms of the habitable zone. And that is because when the sun is really active, and it goes through cycles of activity now, but back in the young stage, it was very active a lot. And we had super flares, possibly. And these things create a huge amount of extra X-ray radiation and ultraviolet radiation, which causes issues with a planet's atmosphere. It basically can break apart molecules when it's intense enough of hydrogen and oxygen, and then atoms, and it basically strips off the electrons because it's so energetic. The electrons can float away because they're lighter, and then in doing so, as they're escaping, they can also interact with positive ions because they're attracted. And so basically you have this ion escape, and the atmosphere can get stripped away from planets. And so you really have to take into account space weather when you're thinking about where that zone is going to be. It's not just as simple as just where the intensity is. So, and the sun will continue to change in the next 4.5, 5 billion years. So, you know, it's nothing static, although on the time scales we're used to, it's very static. But yeah, it's a very interesting dynamic star.
So just to pull on one word you said there, you talked about the habitable zone. So for people maybe not familiar, this is not necessarily a zone in which you are habitable, but it is considered a zone in which the Earth could maintain a roughly temperate climate on its surface. So we are in the habitable zone. Good job. Venus is not. Actually, Mars is in the traditional boundaries for the habitable zone, but being such a small planet, it actually still can't maintain an Earth-like atmosphere, or at least that's one of the reasons. So when we talk about habitable zone and moving the habitable zone, think of it as the region around the star where the Earth would be okay. Now, stepping out one and looking at Venus next. So Venus you have described as really an uninhabitable hell landscape, with temperatures enough to melt lead, incredibly fast speeds in the upper atmosphere that buffet our balloons around. Was that always the case?
It's a great question. You know, I always like to say that, you know, Venus just has had a hard life, but, you know, she started out doing pretty well. Since Venus and Earth are pretty much the same size, they're about the same size and about the same mass. And we think that since they formed in about the same part of the solar system, they probably formed from the same materials. And so very early on in the solar system, Venus and Earth were probably much more similar to each other than they are today. And with that, we believe, based on some measurements and observations from the mid-'70s and late '70s, that Venus used to have very large oceans on its surface. It had lots and lots of water there that is no longer present. And what we think has happened is over time, as Venus warmed up, that water would have evaporated, had gone into the atmosphere, and then through the process that Holly was describing, as the solar wind came by and started trying to strip the atmosphere off, it would have taken a lot of that water vapor away and has taken all of that water, and it's all gone now. So it's now a very, very dry place, or at least we believe it to be so. And I just wanted to say one thing that is a difference between Earth and Venus is that Earth, we have a magnetic field which shields us somewhat from that solar wind and that stripping, but Venus doesn't have that magnetic field. And so, but it's still somehow, because it's such a big planet, is able to hold on to that most of the atmosphere, but it does allow that not having the magnetic field allows those water vapor molecules to be stripped off the outside.
Dave, do you have anything else to add to Venus's early days?
Let me paint that picture just a little bit more for you to fill in a little bit of the dots. Imagine you're here and you have an almost Earth-like environment. The sun is much cooler back then. You're outgassing, you have volcanoes going off, maybe you have some liquid water on the surface, or maybe just a lot of moisture in the air, and maybe just a tiny bit on the surface. But then the sun starts heating up. And then the oceans, if you have them, start to boil. But then the oceans, as they boil, are adding water vapor to the air, and water vapor is a strong greenhouse gas. And that water vapor makes it even hotter as you trap more of that solar radiation, don't let the thermal radiation leave. And now you actually start baking CO2 out of the rocks, and the water vapor keeps coming up and up and up, and it gets to the top of the atmosphere, and the solar wind charges it up, and we also have high temperatures up there that also cause escape of the hydrogen. And how do we know this? Well, we know this because we measure hydrogen, the usual isotope of hydrogen, and we measure deuterium, heavy hydrogen. On the Earth, 1 out of every 10,000 water molecules is a deuterium molecule. And on Venus, it was probably like that too. Now it's 1 out of 100. The fact that deuterium has twice the mass of hydrogen means that it's much more likely to be stripped away by both the solar wind and by just thermal escape. So we know that Venus lost so much water that it enhanced the deuterium-hydrogen ratio by a factor of 100. That is a massive change. And so as Laurie said, it's had a really, really hard life.
So just pulling out one term you used there, greenhouse gas. Now we might have heard that with respect to Earth, where we typically think of carbon dioxide as a greenhouse gas. The idea being that there are gases in our atmosphere that are super good at trapping heat. But as Dave mentioned, water can also do that. Now if we go outwards once again and go into Mars, then we find that carbon dioxide is not as effective there, I believe, because it's starting to condense into clouds and isn't able to trap heat that effectively. But what was early Mars like? Was it still a cold and desolate place, Dramo?
So it's it's funny when we were talking about Venus and talking about Earth, and if you think about it, the two planets were similar in some way at the beginning. And if you think about Mars, actually it was also very similar. It was the same initial conditions. But now you see Venus, it's like a hell. And then you look at our planet, which is perfect. And then you go to Mars, and it's also interesting that Mars also is full of CO2. So you're wondering why the two planets, the nearby planets, one got a greenhouse, ran away, and Mars is also full of CO2. What happened? In the case of Mars, Mars is smaller. And the fact that being smaller allowed to more of the atmosphere to escape, and also the water, which is a good element to control the CO2 going wild, also start to vaporize and also start to escape the atmosphere. So the problem with Mars is they never managed to hold the atmosphere. We actually think that at the beginning Mars had oceans or maybe had a lot of water. Actually, if you were trying to think about life at the beginning, maybe Mars was much more habitable at that time than our planet. Interestingly, we think that when life started in our planet here, in Mars, we think there was oceans of water, or it was much more habitable than it is right now. So the conditions may be there on Mars much more. The problem was that as it was smaller, the atmosphere was, especially the water, which is a key component for habitability, was escaping much easier, and then all that water went away. We think some of that water may be below the surface, but a lot of that water actually flew away from the planet.
Now, I believe we have pretty strong evidence for atmospheric loss on Mars, Dave, because we've actually seen it. Is that right?
We actually have measured it directly. And so there's a spacecraft in orbit around Mars called MAVEN, and it actually has a mass spectrometer on it. So as it flies around, it can actually weigh the molecules that come off the atmosphere. And we're finding that we're still learning quite a bit about how molecules and atoms escape from atmospheres. MAVEN's been a very, very important mission to us. The story isn't entirely written yet, but it's collecting excellent data, and we're finding that the escape rates are a little, let me just say, not a lot faster than we thought they were, but they're different than we thought they were. So we're still trying to chase those questions down.
Well, thank you very much. Now, does anyone have any questions from the audience? Could you come up to the mic?
Hello.
Hello.
Hi. So you mentioned MAVEN and the mass spec that's going around Mars. Do we have one around Earth?
Do we have one or other?
We actually have several. We actually do. We have, there are a series, we've been flying mass spectrometers and electrometers and other instruments that can measure particles coming out of the Earth's atmosphere and actually in the solar wind that we regularly fly. And so we've got several different types of instruments like this flying around the Earth right now. I'm thinking of magnetosphere multiscale and other instruments like that are actually measuring these fields around the Earth, where they're more complicated because unlike Venus and unlike Mars, the Earth has a strong magnetic field. So a lot of the particles are just kind of trapped as they run up and down these magnetic field lines for the Earth. Mars and Venus, Mars, or I should say Venus, because it doesn't rotate fast, has almost no intrinsic magnetic field. So the sun's solar wind just pretty much hits the top of the atmosphere directly. With Mars, it's a little small planet, and it probably did used to have a magnetic field because it spins pretty fast, but its center is kind of frozen solid at this point. So magnetic field's essentially dead. So its magnetic field has gone away too. So on the Earth, we're studying basically the travel of the solar wind around the Earth. That's the main thing, and the tiny escape of our atmosphere. On Mars and Venus, we've had instruments that make similar measurements and are actually watching the atmospheres being stripped away. They're actually comets when you look at them with these instruments.
Yes, of course.
And the beautiful thing about these measurements about the two types of water you can actually measure from here. You can go and measure the two types of water, remote sensing, we call it spectroscopy. So you can actually measure the water on Mars, the two types of water from here using telescopes. Also, you can also look at in exoplanets. So we can look for habitability or escape of water, not only in our solar system, but also far away from here.
So I think Jada has a question from the internet. Is that right?
We've got a question from our online audience. So David Flores asks, is the Mars rover capable of cleaning its own solar panels after a dust storm?
So is the Mars rover capable of doing a cleanup and saving its solar panels from the dust?
I think that's mine. I helped, as I said, I helped design those things. Yes, I have to take responsibility. When we were designing the solar panels for Sojourner, for Pathfinder, and then for Mars exploration rovers, we kept trying to come up with ways of getting rid of the dust. The best maid service we have are the little dust devils that go by at this point. There are ways of getting rid of dust, and you think of them on the Earth, like why don't they just take a little broom or wiper, but there on Mars it's so dry that you know how static electricity kind of makes everything stick to itself when you pull stuff out of the dryer? It's worse on Mars, so the dust just sticks harder as you try to brush it off. We looked at other ways, and some ways were really clever, like we can charge the dust up by just putting a strong field on it and then reverse the polarity. It turns out that that little trick puts the dust into the air very, very nicely, but it can short out your solar panels. But look at it this way, guys. That lander was supposed to last for 90 days and go 1 mile. It's 14 years and counting. I think it's good enough. Even if it's gone, it's lived a really great life. So I think we did our jobs okay there. And
Can I just say one other thing about the rovers, and we'll get right to the question, but I just wanted to follow up. I wanted to agree with you, David, that Opportunity rover has been an incredible mission and just done an amazing amount of geologic field work on the surface of Mars. But I also wanted to mention that we've talked about the solar panels on Opportunity and that's what's kept it from being able to communicate for the last couple of months. You may be wondering about the other major rover that we have on the surface of Mars, and that's the Curiosity rover that I'm sure you've heard a lot about. That rover does not use solar power. So not only is it in a different part of the surface of Mars where it didn't have quite as much dust as the Opportunity rover saw, but it also doesn't rely on solar power. It uses a nuclear power source. And so that's one way to get around the downside of solar panels.
Please.
All right. I have two questions. One's a solar question, one's a Venus question. The solar question is about the coronal mass ejecta.
Mm-hmm.
Can you talk a little bit about the constituents? Is it mostly just protons that get ripped off and thrown out, or is it all kinds of constituents? And are they charged, and do they reach escape velocity? So I want to sort of talk about that. And then on Venus, I'm curious about climate. You know, you mentioned that on the surface, you've got 90 times Earth atmosphere and very hot, but do the mountains of the poles of Venus get much more reasonable in terms of their climate? And so those are my two questions.
So starting with the coronal mass ejection, what is it made of, Holly?
A big bubble of mass. The sun is mostly hydrogen and helium, and in the corona, because the corona is so hot, which is a whole nother weird thing, the atmosphere that's further away from the core is hotter than the surface, and that's a mystery that we've been trying to solve for a long time. But because the corona is so hot, you're right, it's ionized, and so when the material blows out, it's mostly protons, and they're very energized, and these particles get accelerated, and so we don't fully understand that process as well. And it's a pretty neat, weird puzzle of understanding how these things are initiated, again, kind of going back to magnetic fields, but also the composition. And they contain some coolish, relatively coolish material in what we call solar prominences, which is actually what I study in my research. And this cooler material is partially ionized, and these will blow out also with the coronal mass ejection. And so it's kind of a combination, but mostly it's extremely hot material, over 1 million degrees, and it's very, very energized.
So you have like 1 million mile an hour wave?
We so the speed, actually the overall solar wind, which is constantly blowing out from the sun, is 1 million miles an hour. So that's kind of always going on. But these coronal mass ejections are incredibly fast, over 4 million miles an hour. And since they have the density and the magnetic field along with them, that's where you kind of have this powerful storm.
So is it like a wave or like just a cloud?
So the question is it more like a wave or is it like a cloud? And in terms of thinking of it and in terms of a storm, I would say more like a cloud. But of course, the corona is not very dense at all, and so each particle, you're not going to sit there if you're standing in that wind and feel it because it's not dense at all. However, the particles are extremely energetic, and so that's what gives the energy. But yeah, I would picture it more like a bubble or a cloud. And you mentioned waves. There are also waves on the surface associated with these things that are also traveling across the surface. So there's all kinds of cool dynamic activity, and that's what I love to study the most.
So the second question was, the surface of Venus, very unhospitable, but what about a mountainside retreat?
So this is a mountainside retreat, yes. So that's a great question. And let me just provide a little context before I give the answer to the question. So first off, the mountains on Venus are really quite large. And so to go from the average elevation of the surface of Venus up to the tallest mountain is about 10 kilometers or about 6 miles high. So that's pretty large deviation or changes in topography on the surface of Venus. I also wanted to mention that, there's a night and a day on Venus. I think Dave alluded to earlier that Venus rotates extremely slowly on its axis. In fact, it takes longer to go one time on its axis than it takes to go all the way around the sun in one orbit. So it rotates extremely slowly. So there is a day and a night. So now you would think there might be, because of these day and night variations and the changes in topography, that you might see differences in temperature. And there are some, but they're actually very small at the surface, on the order of only a few degrees. And that's because the atmosphere is so dense that as the sunlight comes in and it gets trapped in this dense greenhouse, the heat cannot escape, even through that long night and even over the mountains. And so it's in the lower part of the atmosphere, well mixed, and it's all very, very warm and almost a uniform temperature. We do have temperature measurements down to the surface at some higher latitudes, so we did look towards the poles, and again, we see a little bit of change in the temperature, but not very much. The last fun fact about Venus is that it rotates almost directly straight up and down. Its axis is almost vertical. Earth is on a tilt, Mars is on a tilt, most of the other planets are on a tilt, but Venus is almost straight up and down, so it has no seasons. So the poles really don't get that, they're not really that different from the equator, a few degrees only.
Yeah, so is there any speculation as to why it doesn't rotate like the others?
There's lots of speculation, yes.
There's another bigger thing. If you want me to do this,
My favorite. Well, there's two hypotheses that I like to quote. I don't know that either one of them is any more valid than the other. One is that perhaps there was a major impact early in Venus's history that perhaps hit it just right at the right angle and the right place on the surface to slow it down without tilting it and leaving it in that exactly right tilt. Another hypothesis out there is that perhaps when planets spin up, they can spin up in different directions. They don't all spin up in the same direction because Venus rotates backwards as well. And so as part of that backwards rotation, that perhaps it is going slower and backwards as part of that initial spin up.
I'm going to ask us to move on to another question, so we've got quite a queue coming up.
All right, so we've got another question from our online audience. This one is from Jennifer Haney, and she asks about the consistency of the sand on Mars and if it's different on different parts of the planet.
So sand on Mars, is it like an identical sandbox everywhere, or have we got some serious different geology going on? I'm going to ask Dave to do that.
the sand on Mars is super, super fine compared to the sand on the Earth. There are actually two different particle size distributions that we deal with. We do have granular sand that's about like beach sand, so each of the individual particles is about 1/10 of a millimeter, about 100 microns. And that's one family of sand on Mars that's pretty common. But the stuff that mostly is flying around in the air is much, much finer than that, about 2.5 to maybe, actually 0.4 to 2.5 microns. So 1/10 the thickness of a human hair. Think of it that way. It's finer than any flour that you actually deal with. I've actually tried to make grind up samples as fine as that. It's really hard to do. So yes, it has a couple of populations of sand. When you go to different places, sometimes you'll only find the coarse stuff. Sometimes you'll see the coarse stuff with maybe with right now a nice layer of the fine stuff covering everything. And then after a little while, you'll see a much more segregation.
Yes, and the interesting thing about Mars, so that sun covers everywhere. And interestingly, Mars never developed plate tectonics. So if you actually remove some of that dust from the thing, you're actually going to touch a rock, which is 4 billion years old. It's unthinkable per our planet. So the record of Mars is actually on the surface if we can remove the dust on top of it.
So I'm just going to pull out another term there that you used with plate tectonics. So on Earth, we have our crust is broken up into plates, and these plates actually can slide underneath one another, which means we get a recycling of our material. So if you measure the age of our own rocks, you wouldn't find it at 4.56 billion years. You think it was much younger. But as Geronimo has just said, the rocks on Mars don't have that sinking and rising motion. So what was formed is what you get. Next question.
Howdy. Thank y'all for doing this. So I was struggling to figure out which question I wanted to ask, so I'm going to ask one, and then maybe a bonus if there's dead time. The question is, many of you are interested in exoplanet climates and weathers, and I'm curious about what mechanisms exist to study climatology and weather on exoplanets. And then the bonus question, just for fun, is that I've heard there's some really wicked weather on Saturn's moon Titan, and just would always love to hear more about that.
So exoplanets, we can't go and send a probe around there, so can we say anything about them at all? How do we know about exoplanet environments? Dave, that could be you.
We're trying really, really hard to study exoplanet environments using the best available telescopes, both our space-based assets like the Hubble Space Telescope now, and pretty soon the James Webb, we're hoping. And then we're also using large ground-based telescopes. And what we're seeing there are a couple of things. We're seeing, for example, that a lot of exoplanets have clouds. This is wonderful and, well, a little disappointing, because when there's a solid cloud deck, we can't see anything that's underneath the cloud tops. Other exoplanets have atmospheres that are quite clear, and we can see very deep, and we can actually start to see some of the kinds of constituents that they're made of, but not so much their weather. But there is one kind of weather we can see that's really important that many exoplanets are exposed to, that our nice little neighborhood here is not. Exoplanets we found around a whole host of different types of stars. Most of them are around the smaller stars we call M dwarfs. They're easier to find when they're around very small stars. And those stars, and I'll hand that over to Holly, tend to be really active.
Yeah. So exactly, that again, going back to where that habitable zone should be, because these are smaller and cooler, you expect the zone to be closer in. But because they're so active, and again, they're having these super flares all the time, it actually impacts it, where it pushes the zone out again, because this extra radiation and the extra wind can strip the atmosphere away. So you can't be too close to that. So it's all part of the equation.
So maybe linked with that question, I might just turn to Geronimo and say, when we look at exoplanet atmospheres, it's not just weather we're interested in, it's potentially whether they're habitable. So what are we doing in that department?
Well, actually, the reason that we are actually all here is because we are in a meeting, it's a symposium, that we bring everybody. Actually, we are learning, all of the four of us in this workshop, about climates and other things, and also habitability. So we're trying to find ways to measure. It's not easy because, they're far away. We are looking at the star. We're looking at the star and the planet together, and we're trying to disentangle the two. But there are ways. We are actually finding ways to measure the climate and if they're habitable. So what we're trying to do, how do you understand if a planet is habitable or not? You're looking for some chemical tracers that may tell you that something is happening on the planet. It's a little bit, for example, if you come on Earth and you see a cow, and then the cow produces methane, well, methane you can say, well, maybe it's a biomarker, it's an indicator of biology. It's heavily tailored for our ecosystem, but it's a way to look for life. So we can use similar tracers to look for indicators of biology, or what could be a chemical tracer for something that may be happening on the planet. So what we debate in this conference is what could be the tracers that could tell us that that's the be smoking gun for habitability or being habited, actually.
Can we take the bonus question on Titan?
Yes. So the question there was, we've done Mars, Venus, and the Sun, but what about moons of Saturn, of which the obvious candidate would be Titan?
And Geronimo just set this up perfectly, because Titan is a truly unusual place compared to the other destinations we've been talking about. Titan has an atmosphere on surface that are dominated by ethane and methane. So there's lakes on the surface of Titan, the methane lakes, and atmosphere with ethane atmosphere and clouds. So when we start talking about places that could potentially be habitable, Titan starts to come into view, because at the temperatures of the surface of Titan, during the summer months anyway, the lakes are actually liquid. And so they could actually be places where life could exist, perhaps even today. We don't know whether the methane's being a result of the biology, probably not, but still it's intriguing.
Just to clarify, though they're liquid, we're not talking, 20 Celsius weather, are we?
No, and I can't quote you a temperature on that, but it's definitely
cold, yeah.
sub-zero, yes.
Destroying things. Thank you all so much for being here. So I wanted to kind of piggyback off of the plate tectonics that you were talking about with InSight landing and the seismometer that's going to be on board. So if there isn't a whole lot of plate tectonic movement going on, what are we expecting to see? And my second question is, you were talking about your research earlier. Is that posted anywhere online that can be publicly accessible?
So I'm going to take the first question and unpack that slightly. InSight is a new NASA mission to Mars, and it is going to have a seismometer, meaning that it is going to aim to measure, well, not earthquakes, but Marsquakes. But the question is, without plate tectonics, do we even really expect any of those? Oh, yes.
I'd be happy to take that one. So even though there's not plate tectonics on Mars, there is still a lot of activity we expect on the surface, not the least of which because as the planet has cooled over time, it starts to kind of shrink a little bit. And as that happens, you get a lot of jostling of the rocks and things in the crust. And so we certainly expect there to be some activity and to at least get some measurements of the motion that's present in the crust. In addition, if there are small meteorite impacts, we would be able to measure the seismic events of that as well, or at least the seismic signals of that. So there are a variety of different ways that we can measure activity on the surface, and we expect to be able to do that with the InSight. And that's going to be landing on November 26th, by the way, in a few months.
Now, this is a particularly exciting mission, I personally think, because it's not the first time we've tried to measure Marsquakes, I believe. We've had other missions where we've given this an attempt. Would Dave or Geronimo like to say something about why we're so excited by InSight?
When we launched the Viking landers back in the 70s, we really didn't know what to expect, and we built actually some pretty nice seismometers, very similar to the ones we sent to the moon prior to the time we landed astronauts there. And unfortunately, with the Viking landers, something that we didn't completely take into account is that the seismometer stayed up on a lander that was had 4 legs. The moon doesn't have winds. Mars does. So most of what we built on Mars wasn't a very good seismometer. It was a great wind sensor. Every time the wind blew, we saw a Marsquake, but we never saw anything that could be taken out that was irrefutably a Marsquake. So we know that now, and the InSight seismometers, two different kinds, ones that measure very high frequency vibrations and ones that measure very low frequency vibrations, were specifically designed to avoid wind shock and wind vibration. And they spent a lot of time doing that, and they were very serious about it. So I really expect the kind of actions that Lori mentioned, where we're seeing both the planet's large-scale shrinking. We also, 30% of the atmosphere gets coated out on the poles every year and re-evaporates. And as that happens, we also expect the planet to kind of pop a little bit. And when that happens, it sends seismic waves all the way through the planet. And we can measure those seismic waves very, very carefully and get detailed information about the vertical structure of the inside of Mars. It's the only way to look at it. So that's why we're so excited about InSight.
So, Holly, a question has been posed to you. You're claiming all this excellent research. Prove it.
First, I'm very glad you asked the question because I wanted to compliment you on your Parker Solar Probe shirt. Yes, I know, wasn't it? My research is mostly in journals like Astrophysical Journal and JGR. I can get you those papers. If I have a card, so see me after that. And I've written some review papers and some books, chapters in books. So if you let me know what you're particularly interested in, I'll make sure you can get hold of that. Yep.
What would happen if a coronal ejection had hit the atmosphere of Mars or the surface?
Right, well, there we go, Holly. If a coronal mass ejection smacked into Mars, that would be quite some force. So what do we think would be the results?
Well, I'm more familiar with the Earth and the Earth-Sun coupled system, so I might pass this to my Mars colleagues because I don't know as much about Mars.
So, well, we see the Martian atmosphere being stripped by the solar wind, and we always wonder, do coronal mass ejections mean more, you have this massive energy coming to the planet, they will blow more material. So one of the things that MAVEN, this mission that we sent, NASA mission that we sent, the idea was to investigate how that energy was being delivered and how much more material was being blown away. And we don't know. Actually, I heard some debates recently that say that actually when that thing hits Mars, it produces massive distortions on the planet, but some of the ions actually go back and you don't lose so many ions as we initially thought. So there's a lot of things we're learning with this mission MAVEN. They tell us how that energy is being deposited on the planet and how that energy is being allowed to escape. One interesting thing about it, these storms were thought to be much more frequent in the past. So the fact that Mars we're escaping, this process may be much more prominent and more effective in the past for Mars, and may explain why it lost so much of the atmosphere.
I've got a question about the sun. Two actually. First, the solar sunspot cycle. Can you just comment a little about that and whether sunspots are going away? Mm-hmm. And second is, you mentioned coronal mass ejections and someone else mentioned flares and super flares. How are those related? Are they the same?
Excellent questions. The sun does have an activity cycle. On average, every 11 years, it gets very, very active, meaning the sunspots, which are also magnetic fields. So the sunspots are related to these ejections that I was talking about. Actually, that they originate in sunspot regions. And the more sunspots you have, the more active the sun is going to be. We do not fully understand why it's on average every 11 years that it gets really active. Right now, we're in a period of solar minimum. And except for the last few days, which is great, we haven't seen hardly any activity. And so over the next 2 years, it'll start to increase, most likely. Now, there are some scientists who are thinking, well, wait, this has been kind of a very, very low activity cycle in general. So not only does it every 11 years, but those cycles also have cycles. So some solar maxima are very, 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 very high in terms of number of sunspots and storms, and some aren't. So it's very weird, and it all has to do with this dynamo inside the sun and how that's creating these flows and how that's generating the magnetic fields and how it's doing all this. We have modelers who have ideas about how that works, but we really do not fully understand, unfortunately. So it's job security, I guess. But But we're getting better. Our models are getting more and more sophisticated. So I forgot what the second part of the
What
question.
is the difference between a coronal mass
yes,
ejection,
of
a
course.
flare,
Yes.
and all these things? Are they the same?
They're all related. They're not the same phenomena, and oftentimes, especially in the media, you'll see a prominence erupting where they say, "Oh, a solar flare is happening," and they're two different things, but they're all related to this magnetic reconnection, the interaction of the magnetic fields that causes the flare on near the surface of the sun, which is this explosive. It's the most powerful phenomena in the solar system is the flare, when all these magnetic fields are just bursting, basically converting into very hot energy. But the coronal mass ejection goes away also from that region, but it's a different phenomena. And then solar prominences are part of that. And sunspots are all kind of in that same region. So they're very different, but they are interrelated and oftentimes associated. It's complicated.
Back about the mass spectrometer, I know it's been a bit and a half. You said that what you were seeing was not necessarily different speed-wise, but it wasn't what you were expecting. What were you expecting, and what are you seeing?
So we saw, just to summarize, we saw mass being lost from Mars's atmosphere, but we were surprised by that. But why?
Some of it's just the mechanisms that were responsible for the loss of that mass, and also some of the things I was referring to was the fact that, and Holly touched on that, some of it comes back. So what we found was a lot of the stuff that was being blown off, you would see these big blobs of material blown off in the presence of some kind of a solar storm or increased solar activity. But then we would find out a little later on that stuff just reconnected on the backside. And so in the tail, it basically repicked up. The other things that are going on is actually now we're beginning to study on Mars, as we have on Venus as well, that as the solar wind interacts with the atmosphere, it produces a number of phenomena, including an induced magnetic field. And actually watching how that interacts with itself over time has become a really, really fascinating part of this. And like I said, that's part of it where the story's not completely finished yet. I don't know if you saw in Bruce's presentation yesterday, I missed it, and so he probably had some better news on that. But it is breaking news.
John, do you want to add anything?
So, this mission MAVEN actually has been revolutionary. It's the first time we can actually monitor these particles coming out. And we've seen, if you take pictures of the surface of Mars, you see there was bodies of water there. And it's a big question, what happened with that water? How do you explain all that? So the fact that we have a measurement that is actually measuring those particles coming away, and we can understand what processes are driving that, is really important. It gives us a metric we didn't have before. So it allows us to connect those pictures that we're taking with those escape processes. And I think, it has been so fundamental, these new discoveries, that I think in the next decade or so, we're going to get a much more better picture when we put all these models together of how escape happens also in the past.
Thank you. Let's take the next question.
I had a question about the general engineering process, given that the circumstances of climate and weather are potentially very unpredictable, and also you don't see those things on Earth, and you may not be able to simulate them. So I was curious how much of it is anticipating issues and building for that versus trial and error between missions.
So you mean when you build a mission, how do you prepare for weather conditions that you can't simulate on Earth? Is that the gist? Yeah. Who wants to go first?
I can start with that.
Go for it.
Okay. This is the job security that scientists have at NASA. To some extent, one of our very most important jobs is when we're planning to send a rover to Mars or a lander or a probe to go into the Venus atmosphere. The engineers come to the science community and they say, what can you tell us about this body? What are we getting ourselves into? Is this possible? Is it not possible? How hot is it going to be as we come into the atmosphere? How hard are we going to hit the top of the atmosphere with our probe? How fast will we decelerate? When do we have to actually pull the chute to slow down? Is it going to slow us down before we hit the surface? And all of these are questions that we can answer by running what amounts to climate models, very similar to the ones we run on the Earth, but sometimes a little bit specialized to Mars or Venus, to try to actually learn how these vehicles that we're sending there will interact. And so we get our part. Some of us actually design solar panels as well. How much sunlight, the question that I got was, how much sunlight do we have on Mars when we have a dust storm? That's what they were really worried about. They were saying, well, in the winter, as we go through the seasonal cycle, the sun's changing like this, maybe we can figure that out on our own. But when there's a bunch of dust in the air, how much sunlight's getting through? Does it block all the sun? And the answer is no. It scatters a lot of the light, and so some of the sunlight directly from the sun, the disk of the sun may completely disappear. But the light is just a scattered field, and you know what? Solar panels like that stuff too. So we basically model the rover is sitting at this angle on Mars, and the sun's over here, and I have this much dust in the air. How much sunlight, how much solar power am I generating right now? This is what scientists do to support missions to Mars or to Venus. And it's really an important job, and it's something that all of us end up doing from time to time, often gratis, often as what I refer to as a hobby. So
I mean, Venus is particularly difficult because I think we've lasted exactly 120 minutes down on the surface. So
That's right.
How on earth do you prepare for that?
So the Soviet Union descended to the surface of Venus many, many times, but their world record for survival was 120 minutes. That's correct. Several of their landers survived for about an hour, but the one lasted for 2 hours, and that's about all we can do there. But as Dave says, when the engineers start designing, they come to the scientists and they say, not only what should we expect, but how well do you think you know that answer, right? And so when they say, well, what is the temperature plus or minus what? And what is the wind speed plus or minus what? We need to know, put some bounds on that so that when the engineers start designing their technical design, they can say, okay, I'll go off and run. For example, when we were looking at trying to design something that would go into the Venus atmosphere, and we were trying to figure out how fast it would fall through the atmosphere, they did thousands of Monte Carlo simulations, thousands and thousands of those simulations, looking at the various uncertainties that we had on every single parameter and how they would all work together to influence what that descent profile would look like through the atmosphere. And so then they just have to design something very robust that can survive that full range of possible outcomes. And then as we get to know things better and we get more experience, for example, on Mars, where now we've been through the atmosphere several times, you can start to refine and reduce those little uncertainties, those little error bars, and then you can get a little more sleek in your design and not have to be quite as robust for as many situations.
So
Let me, one thing following.
10 seconds.
Laura. Yeah. So, it's very difficult to land on a planet. So actually the NASA is the only agency who actually managed successfully to land on planet Mars. And the European Space Agency tried to land with an entry descent module in 2016. And even though we know a lot about Martian atmosphere, we know everything about the winds, everything, the sensor was programmed with the program with the range. It thought the winds or the variations in the movement would be around this range, and it moved by 2% beyond that range. That saturated one of the sensors, and the thing thought that it was already on the surface, shut down everything, and it completely crashed into the surface. So, even though we know so much about Mars, such a small little errors can make a dramatic impact on when you're trying to land on something like Mars.
So, last question.
Hi. I was wondering, so you talk about exoplanets and how we can remotely observe them. So are those all just like qualitative, and are there other kinds of instruments that will be able to use things such as Breakthrough Starshot to examine exoplanets like Proxima Centauri b and other solar systems?
So just to recap, of course, we examine exoplanets remotely is the easiest, in inverted comma, thing to do. This is still quantitative because it's a genuine measurement, but is there something we could do to actually get to these planets and take a close-up look?
Go ahead, Dave.
They're really, really far away. Even the longest graduate student career will not get you there. So this is really the issue. Even if we could get there, we would be sending something really tiny, because getting the mass accelerated and getting it all the way there would be really hard, using basically all the power we could possibly muster. And so it'd be a tiny little thing. And then once you get there, let me put it this way. You know that phone call home that you need? You need a really powerful radio transmitter to get that message all the way back to the Earth. Even getting something out to Jupiter or Saturn or whatever takes a tremendous amount of power. So right now, I would say that's impractical. But what we are developing is substantially more powerful ground-based telescopes and space-based telescopes. The kinds of information we gather with those telescopes aren't just pictures, aren't just measurements of the light level. We make spectra. We take the light, we divide it into a rainbow of colors very, very finely, and we measure every color very, very accurately. Most gases and molecules only absorb certain colors of light. So when we see that that color is missing, we say, we got the gas. And we can actually do that for basically everything that absorbs in the Earth's atmosphere, in the Martian atmosphere, in the Venus atmosphere, very precisely. And so we're now applying that same level of techniques to exoplanets, and as we can get a few more photons from those exoplanets and a little bit bigger telescopes, we're going to learn more and more using those techniques. So during your lifetime, that's going to be the way we're going to learn the most, probably.
Do some exoplanets appear to have moons?
Moons around exoplanets, exomoons. Anyone want to hazard a speculation?
Well, there is the idea they are. There are techniques we can use called TTV and other techniques. So you actually look at the transit. You look at the planet. Normally, how we identify the exoplanets, you look at the star, and then you look at the planet going in front of the star. So one of the things you can do is look for some perturbations on those transits, and then by looking at those perturbations, you may infer there are moons on those planets. So there are ways to do it and quantify the exomoons on exoplanets.
So that's a little bit like running a track race with a dog pulling you forwards and backwards. So you go a bit slower, a bit faster as you do that lap.
Correct.
But as Dave pointed out, we have not yet done that. So watch this space.
Yes.
And is that us, Jada? Are we wrapping up?
Yes, so I think we're going to have to wrap up now, but I want to thank all of our really wonderful panelists for this fantastic discussion, and also thanks to our moderator for facilitating this wonderful discussion. Thanks also to the people online who are watching on a variety of social media platforms. We hope you enjoyed this event, and for the people who are here in the room in our live audience, don't forget that we will have some stargazing afterwards from the Houston Astronomical Society. So join us for some telescopes out back near the soccer fields. Thanks, everyone.